Plotting a graph. Plotting a graph may seem a simple skill, but you'd be surprised how many students lose valuable marks on assessed practicals by not doing this task correctly. Firstly, it may seem obvious, but make sure you plot the graph you've been asked to plot. Often, students will plot things on the wrong axes. The first quantity quoted goes on the y or vertical axis. For example, a graph of extension against force will have extension on the y-axis and force on the x-axis. Choose scales that will use most of the paper in both directions. If your scale uses less than half the paper, you can double it. Use sensible divisions such as 1, 2, 5 or 10. Don't have a scale that goes up in 3s or 4s or 6s, etc. Make sure your points use most of the scale. You can start with a non-zero value if necessary. Give your graph a title, which would generally be a graph of your y value against your x value for whatever situation. For example, a graph of extension against force for a spring. I'm going to look at an example using this data from an experiment where the length of a simple pendulum was changed and the time for 20 swings measured. This was done 3 times, and here we found the mean. Here we've divided by 20 to find the time period for one swing, and here we have the time squared in units of seconds squared. We've been asked to plot a graph of the time squared against the length. So here are our axes, and we'll plot the length in meters on the x-axis, making sure we use most of the scale. We needed to go from 0.3 to 0.9 meters, but by including the origin here I can see whether the line goes through the origin, and I'll still be using most of the axis for my points. The y-axis is my time squared in seconds squared, and this needed to go from 1.2 to beyond 3. Again, I've put the full scale on, and this shows the origin, and I still will be using most of this scale for my points. To plot the points, we can use diagonal crosses like this, or horizontal and vertical crosses like this. One benefit of using this type of cross is we can align ourselves horizontally and then vertically for greatest accuracy. I'll show you what this means. First, to plot my point above point 3, I can align myself directly above the point 3 at roughly the correct height and do a vertical line. Now I can concentrate on my vertical alignment and do a horizontal line. Your points need to be very accurately plotted within plus or minus 1 millimeter either side. That means if you're the wrong side of a square on 2 millimeter square graph paper, you'll lose a mark. Now I'll add the other points and join them with a line of best fit. In this case, my line of best fit does go through the origin, and all the points lie pretty close to this line of best fit. If my points were more like this would not be my best line of best fit. It's going too shallow. I should then draw a line something like this, and maybe explain why it does not go through the origin. From experimental data, it will be very rare for a line that should go through the origin to actually go through the origin. Generally there would be some error in your readings causing it to miss the origin slightly. If you have an anomalous reading, like this one, you can ring it and mark it as an anomalous reading, but don't consider it when doing your line of best fit. Here we're back to the original point where the line does go through the origin and through most of the points. To find the gradient of our line, we use as big a triangle as possible, which must have sides of at least 8 centimeters long. So in this case, I can do this as my triangle. The gradient is the change in y divided by the change in x. The change in y is from 0 to 3.6 seconds squared in this case, as x changes from 0 to 0.9 meters. This gives a gradient of 4 seconds squared meters to the minus 1. If your points clearly show a curve, then you should draw a curve, a smooth curve going through as many of the points as possible, and it can help if you turn the paper around so that you are on the inside of the curve, and you can then use your wrist as a pivot and draw a nice smooth curve. Clearly, if on your curve there is an anomaly, you label it and ignore it when drawing your line. To find the gradient of a curve at a particular point, maybe this point, you draw a tangent to the curve and again do a triangle as large as possible. You can then find the gradient of the tangent, which is the gradient of the curve at this point.